So I know some people are still like finishing up their summary, things like that. That's fine. But I want to kind of just talk about some irregularities with electron configurations. And really the nice thing for you guys is you don't have to worry about them anymore. So irregularities used to be tested, and then as of last year, they said you don't have to know them, so you don't have to know these anomalies. So some examples, and I know I talked about them in the video, but copper, silver, gold, palladium, chromium. So these are the predicted configurations. So you notice there's like S2D9, S2D8, or S2D4. And normally, what we would do is we would have to half fill some of the higher level and completely fill some of the lower level. So we take from S2 to D9 and go S1, D10. So these are the actual configurations. Now, these are no longer tested. So if I ask you to write the configuration for palladium or for chromium, you write it just like you would based on the periodic table. So S2D8. You do not have to know these anomalies anymore. Now mastering might ask you for one of them or two of them because mastering goes on what it's supposed to be. But just know that you do not have to know these irregularities for quizzes and for tests. So makes it a little bit nicer. Switch this over. With electron configurations, as long as you have a periodic table, hopefully you can write a configuration. And I like to tell people that electron configurations, when it comes time for the AP test, should hopefully be quote-unquote easy points. Just because I try to do them whenever I can. I try to tie things back to electron configurations. So the first couple of things we do actually are from the notes, and so you don't have to write this in your notes. You can still do it on the desk. But this is on page 10, so it's right underneath the example that was done in the video. So in the video, there was an example, and then there were some practice problems underneath it. And so this says use the periodic table to write the complete and noble gas electron configurations. So if it specifies complete or noble gas, make sure that you're doing the correct configuration. If it doesn't specify, do either one. Most people do the noble gas with a shorthand because it's shorter. So we're going to start with cobalt. So we need complete and noble gas. So I'll start with the complete configuration. So complete means we start all the way at the beginning with 1s and work our way through. So if we look at the periodic table, hydrogen and helium are the 1s, so we have 1s2. What comes after 1s2? 2s2. And then we work our way over to what? 2p6. Right, then we come down to 3s2. Work our way over. Aluminum starts the 3p, and then it's 6. Because there are 6 if you count over. P can hold 6 electrons. Then we come down again to 4s2. Now cobalt is in this next row, so we have to count over. 1, 2, 3, 4, 5, 6, 7. What sublevel is this? What comes after 4s? 3d. So over here, I don't want to write on this periodic table with this marker, but this is the S block, right? The P block, the D block is in the middle, and F is down at the bottom. We will look at one F configuration today. Remember that for the D block, it's always n minus 1. So n is the row, right? Here's n equals 1, that's why it's 1s. N equals 2, 2s and 2p. When you get down to the D, you have n minus 1. F is n minus 2. So here's the complete configuration. Noble gas, or the shorthand configuration, means that we look at the noble gas immediately before. So find cobalt. The noble gas immediately before cobalt is what? Argon, Ar. So we're going to put Ar in brackets. So argon actually takes the place of all of this, which is why if we have the chance to do a shorthand notation, most people usually do. So argon will take this entire part of the configuration, and then we just finish it. 4s2, 3d7. But please make sure that you're reading the question just to see if it does specify the type of configuration that you need. So see if, and if you want to like turn around and talk to people around you, you can, but see if you can go through and do the complete configuration for Te. So find tellurium, which has the atomic number of 52. See if you can write the configuration. We're not quite getting down into the F block yet. So here's what I noticed that most people will miss. You go from 4s to 3d, but don't forget that then you have to go back up to 4p. The d block is n minus 1, but then you just continue on. So 4p, then 5s, then 4d, then 5p. So I always, like in honors, I would always say you read this like a book. Start with 1s, right, and then you work your way through, just remembering that the d is n minus 1, and then it comes back. The p is based on the level. D can have 10 electrons, so if it's filled, you should see a D10. Now, the noble gas immediately before tellurium is what? Right, krypton, Kr. So for the noble gas, I'll have krypton, and krypton will take all of this into account. So instead of writing from 1s all the way up to 4p, we could just put Kr in brackets if it allows us to do noble gas. Then 5s2, 4d10, 5p4. So if this were a problem that just said, write the electron configuration, you pick which configuration you want to write, longhand or shorthand. Most people choose shorthand because it's shorter. Okay, so that's just looking at the complete and the noble gas configurations. Now, I'm going to actually leave this up here. So this is the last part of the question that's in the notes. And so it says, draw the orbital diagram for cobalt. So I left the noble gas notation right here that we just wrote, because it'll be useful. All right, so I left this noble gas notation. So the first thing it wants us to do is draw the orbital diagram. Then we're going to relate it back to quantum numbers. So now we'll actually be able to look at how quantum numbers really tie into an orbital diagram. Now, if it does not specify orbital diagram, or what type of orbital diagram, use shorthand. Use a noble gas. That's why I left this. So I'm going to do argon in brackets. And then for my orbital diagram, the orbital diagram is where we're essentially looking at the picture. So I'm starting with 4s. Now, I don't care if you want to use boxes or you want to use lines. What I do care about is that you have the correct number of them. Any s sublevel, 1s, 2s, all the way up to 7s, only has one orbital, which means it should only have one box. The d sublevel. The d sublevel has how many orbitals? 5. So 1, 2, 3, 4, 5. Even if they're not all filled, you still need to show all of the boxes. I always just draw one big one and put lines through it. You could do 5 individual boxes, that's okay. But here's kind of what the basis of our orbital diagram will look like. So 4s2 gets filled first. I use these half arrows. Whether you use the half arrows or the whole arrows, it doesn't matter. So 4s gets filled first, and then 3d7. Watch how I fill this if you forget orbital diagrams. 1, 2, 3, 4, 5, 6, 7. One in each, and then they pair up. So here's the orbital diagram for cobalt. And then it wants to know the 4 quantum numbers of the last electron that was added. The last arrow that I drew is this one. So when we think about the 4 quantum numbers, N is the main energy level. So this right here, this 3D, tells us the first 2 quantum numbers. So N is this large number, so 3. L is based on the sublevel. So if you remember, L starts at 0, goes up, S, P, D, and F. So this electron is in the D sublevel, so L is 2. M sub L is the magnetic quantum number that describes the specific orbital. This is always how I do it with orbital diagrams. Find the middle box, that's 0. Work your way out. So the specific orbital that this electron is in is -1. And M sub S is the spin. You only have one of 2 possible numbers, +1/2 or -1/2. Right, this is minus because it's pointing down. So that's how we can relate quantum numbers to the orbital diagram. It always will ask what are the 4 quantum numbers for the last electron that is added, which is why you want to make sure that you're filling everything appropriately as well. Okay, so that's it for the practice out of the notes. All right, so then we're going to kind of tie it all together. So for each of these, we'll kind of just go through one at a time. So we'll start with iron. I'll start with Fe. For iron, we're going to write the electron configuration. Now notice how it just says write the electron configuration. You can pick longhand or shorthand. Most people tend to pick shorthand. That's the noble gas notation. Then draw the orbital diagram, and then write the quantum number of the last electron that was added. So see if you can go through and at least do A and B for iron, for Fe. Okay, so if you want to double check, I did the configuration and the orbital diagram. I circled the very last electron that I added, because for the quantum numbers, that's what we're doing. So when we look at quantum numbers, it goes N, L, M sub L, M sub S. 3D tells us both N and L. So we have 3, so starts at 0, 1, 2, right? SPD. So L is 2. L is always based on the sublevel. And then if I look at the orbital, I just start with 0 in the middle and I work my way out. So the magnetic quantum number is -2, and then spin is always whether it's pointing up or down. Pointing down, it's -1/2. Okay, so if you want to try palladium, you can. I want to focus on uranium, so I want to make sure that we get as much of this practice done as we can. So the next one that I want you guys to look at is uranium. So electron configuration and orbital diagram. Uranium's atomic number is 92. Uranium's atomic number is 92. We're going through this one because if you look where uranium is, I want to be able to go through the specifics of what happens if we get down to the F block. So the first thing to do is if you find uranium. So uranium is all the way down here in the actinide series. The actinide series actually, it technically belongs right here. So the periodic table should actually be a lot longer than it really is. They pulled the lanthanide actinide series out so that they could condense it down. So we find uranium, it technically belongs down here in row 7. What is the noble gas that would come immediately before uranium? If it technically belongs at n equals 7, what's the noble gas that's at the end of n equals 6? Radon. Right, so we're going to put Rn in brackets. So we'll put Rn in brackets, and then we'll start to continue the configuration. 1, 2, 3, 4, 5, 6, 7. So row 7 starts with 7s. Now here's where it gets weird. And I have it marked on the periodic table that's hanging up here. I actually went in with a Sharpie and I wrote the D and the F. AC, actinium, which is an atomic number 89, if you notice where it is even on your periodic table, actinium is in the D block. That technically starts the D block. So 3, 4, 5, 6D1 is actinium. And then I start in the F. 1, 2, 3. So 4F, 5F, 3. So when you get down in the F block, the configuration will look a little bit weird. And that's because I have not completely filled the D yet. I put one electron in the 6D, and then I have to start moving on to the 5F. So now if we look at the orbital diagram, so 7s, we know that S has one orbital. The D sublevel has how many orbitals? 5. 1, 2, 3, 5. And how many orbitals does the F have? 7. 1, 2, 3, 4, 5, 6, 7. So now the way that this actually gets filled is that we're going to put one electron in the 6D, and we're going to put 3 in the 5F. We put 1 in each orbital before pairing them up. And that's the electron we're going to write the quantum numbers for. So this 6D, like this D and F difference, is when you're actually writing the configuration for an element that is in the F block. If we're writing the configuration for something like lead or bismuth, anything that's over in the P, we'll fill the D and the F. You don't have to worry about anything else. So then we're going to write the quantum numbers for this electron. So remember that 5F gives us the first 2 quantum numbers. So n equals 5, SPDF, 0, 1, 2, 3. And then for the orbital, I just start at 0 in the middle, work my way out. So -1. And if it's pointing up, what's the m sub s value? +1/2. So again, that's tying the quantum numbers to the orbital diagram. Now, I want to go through Zn2 plus together, and then I'm going to have you guys do Na plus on your own. So I want to come and do Zn2 plus together, and here's why. When you create an ion, whether it's a cation or an anion, when you create an ion, something is either gaining or losing electrons. Anions, when you're creating a negative ion, you're just adding electrons to empty orbitals. Cations are a little bit different because you have to remove the electron from the highest value of n. So your highest energy level is going to lose the electrons. So for Zn2+, I want to start by just writing the configuration for zinc. So I'm going to start by just writing the configuration for zinc, just neutral zinc. So immediately before zinc is argon. 1, 2, 3. So then we have 4s2, 3d10. So that is neutral zinc. That's just Zn. If it's Zn2+, what is happening? How do we create the 2+ ion? Losing 2 electrons. Because we're creating a cation. When an atom loses electrons, they have to come out of the highest value of n. In this case, my highest value of n is n equals 4. So you have to remove the electrons from the 4s first, then you can start pulling them out of the 3d. So if it loses 2 electrons, it's going to lose both of those. Which means the configuration for Zn2+ is going to be argon 3d10. Now what if this was Zn3+? Well, then you'd remove 2 from the 4s and then 1 from the 3d. Okay, so I just wanted to look at the specific configuration. You can keep going with the orbital diagram and quantum numbers if you want more practice with that. I want to make sure we get more practice with configurations. So go ahead and do Na+. Just focus on the configuration. Right, just write the configuration.
So it's like a...
Yeah, so if you're taking out, you're creating a cation of something that has S, then F and D as well, you're going to always remove from the highest value of n. So whatever the highest big number is, you remove out of that first, then the next highest number, then the next highest number.
What if you have a P or an S and a P value that they have the same?
So then you'll remove from P first and then S. Yeah. So that's like when you create, for example, like an Al3+ ion, the aluminum has 3s2, 3p1. You'd remove 1 from the P and then the other 2 from the S. Yep. So for Na+, I always like writing the neutral atom first. Now here's the thing with this. So Na, neutral Na is Ne3s1. If it's Na+, how many electrons is it losing? 1. So it's going to lose this 1 electron. You can't just write Ne in brackets as the configuration. Sorry. So if it has the same configuration as neon, then you would have to do helium in brackets, 2s2, 2p6. All right, can't just put Ne in brackets. Sorry. So that's just looking at some configurations. We'll do a little bit more with configurations of ions in the do now over the next couple of days. Any general questions on these configurations? Right, so if not, I'm not going to have you do all of these, but I'm going to have you pick. Let's actually do 9, 10, and 13. So cesium, nickel, and lead. I said to write the noble gas configuration, so that means you need to have the shorthand configuration. So again, we're going to do 9, 10, and 13. So cesium, nickel, and lead. All you're doing is the configuration. You don't need the orbital diagram, you don't need quantum numbers, just the noble gas or condensed or shorthand configuration. And these are all neutral, right? They're not ions, they're just neutral. So cesium, nickel, and lead. And remember, we're not doing any irregularities. You're going to write the configuration just as it would be on the periodic table. So the biggest one is lead. Now, if you switch the 4F and the 5D, that's okay. Right? That's not a big deal. But they are both filled. Don't forget about the F. So atomic number 57, and if you notice, 58 to 71 comes down to the 4F. Then the 5D, then we go back to 6P. So now here's a question, right, that Mike asked about what happens if we have a cation and we need to remove electrons. So let's use lead as an example, because this is a really good example of having all of these different values of N. So let's say that we want to form Pb4+. You have two possible ions for lead, 2+ and 4+. Well, if it's lead 4+, how many electrons are being removed? 4. So we have to remove 4 electrons. Well, if you look at this electron configuration, what is your highest value of N? 6. My highest value of N is 6, and we have 6 here with the 6P, and we have a 6 here with the 6S. So we're going to start by removing from the highest value of N, but then we want to go to the highest sublevel within that. So here's 2 of the electrons. I'll remove those 2. The other 2 electrons would get removed from the 6S. And so then if we wanted to write Pb4+, we would have Xe, 4F14, 5D10. So you always remove from your highest value of N, and then, like let's say this was 5+, which we wouldn't normally see 5+, but if it was 5+, then we would remove the next one from 5D10. Okay, so that's looking at some more noble gas configurations. The last thing that I want to look at are more of these AP-style questions. Now, AP does ask you questions like write the configuration. There are many free response questions that are write the electron configuration for this atom. But they also ask some questions like this. Right? When you look at this, you're like, what? So this says identify the group of elements that corresponds to each of the following generalized electron configurations and indicate the number of unpaired electrons for each. So essentially what this wants us to do is it's just giving a generalized N value. And it wants us to give the family, it wants us to give the family that this represents. So NS2, NP5. Right, this could be 2S2, 3S2. So just look at, like, let's say, plug in a number. Let's say this was 3S2, 3P5. Well, look on the periodic table and see 3S2, 3P5 would put us at C up. Now this one's the group of elements. So what if it was 2S2, 2P5? Maybe fluorine. So that entire group is known as what? Halogens. So this configuration describes the halogens. And then it says indicate the number of unpaired electrons. So if I look at the orbital diagram, if I'm assuming this is 3, right? It doesn't matter if it's 3 1, 2, 3, 4, 5. How many unpaired electrons are here? Just one. So 1 unpaired electron. So we look at 15. ns2 n minus 1d squared. Now we know that n can't be 3 because there's no such thing as 2d. So let's say this was a 4. 4s2 3d2. Say d squared. d2. So 4s2 3d2. Look where that would be on the periodic table. 4s2 3d2 would be titanium. Well, what if n was 5? 5s2 4d2. Zirconium. So I'm just going to say it's titanium's family. So it could be titanium, zirconium, right? Anything in that family. And if you draw the configuration or the orbital diagram, right, if this is D and there's only D2, how many unpaired electrons are there? 2. And then if we look at the last one, again, plug in a number. We know this can't be 1 because we can't have 1p. This can't be 2 because we don't have 1d. Right, the first value we could actually put in here is 4. So if this is 4s2, 3d10, 4p1, 4s2, 3d10, 4p1 is gallium. Now again, it can't be aluminum or boron because there's no D in front of those. So this could be Ga, In, or Tl. And if I look at this, these are both filled. So how many unpaired electrons would we have? 1. And if you want to draw the orbital diagram, just to double check, you can. Right, but there's only 1 electron.
How could TL be one of them?
Yeah, so if we're assuming that they need to show F, then we could just do Ga and In. So we could just do Ga and In, assume that they have to show F for it to be TL. Yeah. Okay, so that's it for the practice. I just wanted to go through additional practice. You'll have more time to practice tomorrow. The only thing for tonight is just to work on mastering. If you have the microfiber cloth and you want to put it in your lab drawer, you can. If you prefer to just keep it in your bag, that's fine too.